Today we're going to talk about graphing the derivative of a function. And we're going to start off with some really easy ones and then move into some that get a little more difficult because we don't actually have the equation of the original function. So if you're asked to graph the derivative of f of x equals x squared minus 2x plus 1, we already have the equation of the function, so we should just be able to take its derivative using the power rule, get 2x minus 2, and then just graph that function. So 2x minus 2 just has a y-intercept of negative 2 and a slope of 2. And it's just that simple. What we're going to do is a couple more of these, and as we do those couple more, we're going to sort of look at the relationship between a function and its derivative and what the graph of a function might tell us about the derivative, or what a graph of a derivative might tell us about a function. So here we've got x cubed minus 3x. Again, we're given the equation, so really easy to find the derivative of that. F prime is 3x squared minus 3. And, well, to graph 3x squared minus 3, we know it's going to have a y-intercept of negative 3, because that's the constant term at the end of the polynomial. And 3x squared is a parabola that opens up. We can see exactly where it crosses through the x-axis by just solving this. So setting it equal to 0 gives us x squared equals 1, or x is plus or minus 1. So it must be crossing through the x-axis at positive 1 and negative 1. And it's just a parabola that's going to open up. Our next one is a nice easy polynomial again. In order to take the derivative of this, we'll just, again, use the power rule. So f prime of x is equal to 4x cubed minus 10x. And, well, the y-intercept, since there's no constant term, must be 0. And we'll see that, that's an x and a y-intercept when we factor out a 2x, leaving us with 2x squared minus 5. And if we set that equal to 0, we get x equals 0, and x equals plus or minus radical 5 halves. And radical 5 halves, well, 5 halves is between 1 and 4, so its square root must be between 1 and 2. So we're looking at another x-intercept between negative 1 and negative 2, and between 1 and 2. I'm not too concerned about exact values right now. As we graph these derivatives, most of the time it's going to be just a general idea, just a general sketch of what the function looks like, not necessarily a perfectly exact representation. We need to know a couple more things about this. One is the cubic, and cubics that have a positive a value should always be falling to negative infinity as we go to negative infinity, and going up to positive infinity with probably some little local maxima or minima in between. Now, we don't yet have exactly all the knowledge about where those maxima might occur, but we could guess that the derivative should have a value pretty equal to the average rate of change along this piece of the curve, since that's what a derivative is. So if I were to, let's say, take a look at what I thought the slope was right here at x equals negative 1, at x equals negative 1, it looks like the slope of the function there is maybe around, I don't know, 3, 4, 5, somewhere in that range. So I'm just going to plot a point for my derivative up there at negative 1, about 4. And I can do the same thing down here, about maybe a slope of negative 4 there, positive 1. And we'd be able to sketch our graph going through like this. So now that we've got a couple of functions with their derivatives graphed, let's take a look at a few important things that we need to know here. The first is that if we take a look at the first function, it sure looks like when our derivative, our line in red, was equal to 0, this function has a local minimum. Okay, so when f prime equals 0, we had a local minimum. If we look at this one, when our derivative was equal to 0 at -1 and 1, right here, and right here, our original function had a local maximum right here and a local minimum right here. So again, when f prime was equal to 0, we saw a local max or a local min on f of x. And this is something we've talked about before when we were looking at horizontal tangent lines or places where the derivative was 0. We were getting a local maximum or a local minimum. And that should hold up again as we look here. Everywhere where my derivative is 0, my function has a local minimum or a local maximum. So once again, it appears that holds up and is true. Beyond that, it would be good for us to notice that to the left of this x-intercept of my derivative was negative. Okay? Down here, f prime of x is negative. And we'll note, we'll note that when f prime was negative, our function was decreasing. Decreasing is D-E-C. And after the place where our derivative was 0, where our derivative was positive, our function was then increasing. So when f prime was positive or greater than 0, f was increasing. And if we look at the next two graphs, we should again be able to see that. That everywhere where my derivative in red here was positive, so from negative infinity coming down to -1, it would appear that my function in black here was increasing when my derivative was positive. But everywhere where my derivative was negative, this section down here, the function itself was decreasing. And once again, where my derivative became positive again, my function started to increase. And we can take a look here as well. Same concept. My derivative was negative right here, so my function decreased. As soon as my derivative changed to being a positive value, my function was always increasing. And as soon as it changed again to a negative value, my function began to decrease and decreased on that interval. And as soon as our function's derivative was positive again, the function began to increase. And so that should hold up for any function, which makes sense because if a derivative is greater than 0, that means that the function f has a positive slope. Well, what do we know about positive slopes? We know that when the slope's positive, the function's going up. Right? And vice versa, if f prime was less than 0, f has negative slopes and should be going down, should be decreasing. We got one more thing that would be good to notice, and it has to do with the concavity of our functions. So we'll actually start here this time on this 4th degree function. Our original function is concave up on this interval, and then right here, it switches and becomes concave down. We call that a point of inflection. We'll talk more about that in a second. But on that first section, before that point of inflection, As we're going from negative infinity to here, whatever value that happens to be. Looks like it's about around -1. Our function is concave up, and our derivative is increasing. As soon as our function switches from being concave up to concave down on this interval right here, our derivative then is decreasing. And if we look again, here our function switches back to being concave up, and our derivative is now increasing again for the rest of its domain. And that's something else that will hold up as well. If we look back at the first function, our parabola is always concave up. Right? This is a is greater than 1 parabola. It's always concave up, and its derivative is always increasing. So that still holds. And the same is true on the second one we looked at. When my original function was concave down, my function, its derivative, decreased. And when my function was concave up, the derivative was then increasing. So these are some of the important things that we're going to need to remember about the relationship between a function and its derivative, especially when looking at the graphs. So first, we've got that any minimum or maximum on the graph of f should translate to an x-intercept on the graph of f prime, assuming our function is a continuous function. Okay. We've also got that any point where the graph of f changes concavity should be a local minimum or maximum on the graph of f prime. So our graph changed concavity here, and we had a local max. Our graph changed concavity here, we had a local min. If f is increasing, f prime is positive. If f is decreasing, f prime is negative. And lastly, we'll want to note that any point on the graph of f that has a cusp corner discontinuity or vertical tangent line will have a discontinuity on the graph of f prime, because these were the 4 reasons why f prime does not exist. We didn't see that in the first ones because they were all polynomials, but it will apply to some of the ones we're going to look at here in a minute. So if we're looking to graph the derivative here of f of x, our derivative is clearly just a line with a slope of 2, which means that its derivative, slope of this function, is always 2, which means that the derivative should just be a continuous function that always equals 2. And it makes sense that our derivative is never equal to 0. Therefore, our function should never have a max or a min. And it also makes sense here that since f prime is always positive, it's always 2, our original function should always be increasing, which it is. For this next one, the first thing that we'll note is that we have a local minimum on our graph at x equals 3, which should translate to an x-intercept on the derivative. So here's f of x, and we're going to do f prime of x in red with an x-intercept there. If the original function is decreasing, that must mean that the derivative is negative until we approach that x-intercept. And then afterwards, since our function is increasing, our derivative must be positive. Now, this is where you have to just kind of estimate approximately what those values are. So if I were to look at maybe x equals 2 right here, and just sort of ballpark what the slope here was, it sure looks like maybe it's maybe -3 or -4. So somewhere around -3, -4 is close enough. And the same goes over here at the next x value over here, 4. well, it looks like it's about 3 or 4, so we'll just kind of go up about the same amount. And we'll just connect this in a nice line here, because we know this looks like a parabolic function, so its derivative must be like, and it follows all of our rules. When the derivative is negative over here, the function decreases, and vice versa. When the derivative is positive up here, the function is increasing. For this one, again, we're going to take a look at where our original function, f of x, has a local max and a local min. And it looks like we've got a local minimum here at x equals -4. So that'll be an x-intercept. And we should have another x-intercept over here at about x equals 2. Our function starts off decreasing, which means our derivative needs to start out negative. And if we just went over here to maybe around, I don't know, let's say this point, looks like that slope is maybe -4, -5. So we'll throw a point down there at around -4 or 5. And as we get a little closer, we can see that the slope here is closer to about -1. So we'll just throw in a point here. That's about -1. And we'll do the same thing over here where our function is again decreasing with a negative derivative. And it looks like it's kind of decreasing at about the same rate as before. Looks like over here it's about -1. And a little further over, maybe closer to -4 or -5 again. So we'll just come over here and plot down a point. And maybe another one a couple of units over around here. Now, what's happening in the middle? Well, our function increases, which means that the derivative must be positive. And it looks like that derivative maybe at a maximum makes it to a slope of about 2. So right in the middle here, we should be at about 2. And that seems about right, that our function changes from concave up to concave down at that point. So it should be giving our derivative a local maximum. Could have been a minimum, but based on the nature of the function, it ended up being a local maximum. This one's even easier. First thing we'll note is that we have a corner, right? Anytime we have a corner, we know we're going to have a discontinuity. So to the left of that corner, this slope along this part of this function is always -1. So our derivative is -1 until we get to the x value. And that wasn't very good on -1 there. We'll try to get a little more accurate. Until we get to that x value of -2, where we have a discontinuity. Then we switch over, and now this piece of it has a slope of 2. So we'll jump up here to a slope of 2. And that's what our derivative looks like. Got another slightly complicated looking one here. As we look, coming in here, our original function is decreasing, so our derivative should be negative. And it looks like it's starting off at a pretty small negative value, like -1/3 or -1/2, and slowly increasing up to maybe a maximum, or well, smaller than that value of -2. So we'll go from about -1/2 or -1/3 over here, about -2. When we hit this cusp, right there, we have a discontinuity, and we switch to a slope of about 2. That goes out to about the slope or 1/3. So we'll start around 2 and bring it down here to about a slope of 1/2 or 1/3, where we're going to have a second discontinuity because our function has a jump discontinuity on it. And then now it becomes piecewise linear with a slope of -1, followed by a slope of 3, followed by a slope of 0. So we'll just have a couple of jumps there. The first one goes down to -1. We jump up immediately to the slope of 3, and then we jump down here to a slope of 0. And this is the last one we're going to look at today. We'll start by noticing that our function is increasing, which means the derivative is positive. It starts off maybe close to about a slope of 4 or 5. And then by the time we get down to where we're going to have our x-intercept, it's got a slope of 0. So we'll come in here around 4 or 5 and come on down till we hit that value at 0. And here where our function decreases and changes from concave down to concave up, we're going to have some negative derivative values as well as a local minimum. And it looks like in the middle there, maybe it gets to about a slope of -2. So we'll kind of right there in the middle, drop down to about a slope of -2, where we'll come back up. This looks like about a slope of +1 there. So we'll come down to -2 and then back up to a slope of 1. And we're going to end our point there and have a discontinuity here where we've got that corner. And at that corner, we switch to a slope of -2. So we'll drop straight down to -2. Continue there till the next corner where we turn into a slope of 1 along that piece of the linear function. And it stays as 1 for the remainder of the domain. So now we have a little bit better of an idea of how the function and its derivatives are related, how their graphs are related. And we're going to use this information next time to be able to take a function and use the derivative and also the second derivative to accurately graph with appropriate x-intercepts, y-intercepts, asymptotes, correct local minima and maxima, correct points of inflection, without having to use a calculator for any of it. But that's it for today.